for mean value theorem, let me give you the bigger picture, and then we will go into what it actually means mathematically and how we figure that out. Let's say that we start with a graph of distance from home, and I'm going to call that distance y. And let's see how it changes over time. So, you leave home and you're driving at a certain speed, your speedometer says something, and then you go to work, and then you spend a little time there, and then you remember that you forgot to pick up your friend, and then you go to your friend's house, which happens to live closer to your home than your work is, and then your friend is not there, so you decided, hey, I'm not gonna work today, and then you go back home. So everything is one ride only, and it happened over a certain period of time. I don't know, let's say 1 hour or 2 hours. Anyhow, whenever you have two different periods of time, let's say that this is, I don't know, 15 minutes, and then this is, I don't know, 50 minutes later, you know that in average, if you cover this much distance over this much time, then you have an average speed. Okay, in this case the average speed is going to be negative because you seem to be going towards home rather than away. If you were away from home, that would be a positive velocity, and if you go towards home, that would be a negative velocity, because the distance is not increasing from home, the distance is decreasing. But you know that this will be average speed. It will be the delta y over the delta in time. And so what the mean value theorem is, in this case, mean meaning average, what it says is that if in average your speed in here, or your velocity, was, I don't know, let's say that you went from mile 7 to mile 5. So it says that if you went 2 miles in the space of 35 minutes towards home, right, because it's negative towards home. So it says that within that trip between minute 15 and minute 50, between this point and this point, there is some moment in part of this trip for which your speed was exactly negative 2 over 35. So in here, for example, this point has a velocity that is, to begin with, positive, which doesn't look at all like this one. But and for example, this one has a velocity that looks like this, not at all like this one that is the average. But I have to guess that a point over here will have a velocity that actually has the same value as the average one. So what the theorem says is guarantees the existence of such moment, of such point, for which the derivative is exactly the same as the average rate of changing here. So between the minute 15 and the minute 50th, I don't know, we don't have an exact way of finding it yet. The theorem doesn't provide that, but the theorem does say that there is a point in here, and it doesn't have to be in between 15 and 50. It's not the middle point between those two, but there's got to be some point C in here for which the derivative is just worth the same, negative 2 over 35. So let's talk about what it is, what's necessary to define before proving something like this. We're not going to prove it in this part, but we're definitely going to see applications on that. So let's start with the slides, and let me explain to you what the theorem here is, what is necessary to prove the mean value theorem. And the book talks about Rolle's theorem. So I'm going to start sketching these steps, and you're going to see how it makes sense to have this set of hypotheses. So let me just work side by side here, and well, maybe not side by side, but one above and one below. Okay. So it says Rolle's theorem, let f be a function that satisfies the following three hypotheses. So number one, f is continuous on the closed interval AB. So I have some numbers AB. So I know that f is going to be a continuous function. So it has to start in here and then maybe go like this. And ends here. Okay, so I have A and B as domain, and my range is, you know, all these values, and it's continuous. So that is check. Now part 2 says f has to be differentiable on the open interval. So no corners or cusps or pinches. Now in here I have a pinch, so I better get rid of it. So that one wasn't a good example of function. So let me just make it smooth. So now it's differentiable. Check. Now f of A has to be the same as f of B. And it's like, okay, f of A is over here and f of B is over here. So I didn't do it right. Let me just fix it. F of A and f of B have to be the same. So now they are. So that condition is met. So now that I have the three conditions, it says then there is a number C in between AB such that the derivative is 0. So you know how when the derivative is 0, it looks like the tangent line is a horizontal line. So actually I do. For this point, f prime is 0. And so is for this point, and for this point, and for this point, and for this point in my example. So not only that I have one value for C, I have several values for C. So the Rolle's theorem guarantees the existence of at least one of them. In my example, I have several, so you could have several, but at least you should have one. And this is true as long as these three conditions are met. If the three conditions are not met, then we cannot guarantee of such a point. So this figure is showing you different examples of functions that meet the three conditions, the three hypotheses, and how many C's you can find. If the function is constant, then every single point has derivative 0. So every single point is a good value for C. In here in this function, notice how f of A and f of B are the same, and there is only one value for C. That in that point the derivative is 0. F of A equals f of B, and now I have 2. I may have 1, I may have 2, I may have infinitely many. In here also f of A is the same as f of B, and you can see how there is a point here for which the derivative is 0. So it says, in each case it appears that there is at least one point on the graph. Okay, so this theorem, although we have improved it, we know that it makes sense as long as the three hypotheses are met. For example 2, you can read the explanation yourself, or you can listen to what I have to say about this. It says, prove that the equation x cubed plus x minus 1 equals 0 has exactly one real root. So I'm going to use the intermediate value theorem. And this is something that we have learned before, and remember that you know, we used it for roots mostly, and it said pretty much that if you have a point, you know, below the x-axis and one above, and your function is continuous, then there is no other way to have a continuous function through those points than to cross the x-axis. So it guarantees that there is a value in here in the middle for which a value C for which f of C is 0, given that you have a positive and a negative one. It doesn't have to be for positives and negative ones. It could have been for any value in between. Like for example, if f of A is 2 and f of B is 3, and this is a continuous function, then there's got to be a number C for which f of C is 2.5, or any value in between 2 and 3 because of the continuity. So I'm going to use this theorem to show that there's going to be at least one root, and also I'm going to use Rolle's theorem to show that there's no other way but just to have one and not more. So okay, so intermediate value theorem, I'm going to choose and two x's. I'm going to choose x equals -1, and I'm going to choose x equals 1. And then I'm going to find f for those values. F of -1 is -1 cubed plus -1 minus 1, and that will be -1 minus 1, -2 minus 1, -3. And then f of 1 will be 1 cubed plus 1 minus 1, and that is 1. Since f of -1 is -3 and f of 1 is 1, and this is a continuous function, I'm not sure what happens in the middle. Well, I am sure what happens in the middle because this is a cubic function. But regardless of that, of what happens in the middle, I know that if this is continuous, there is gotta be at least one point. Maybe it's like this. At least there is a point in which f of x is 0. Okay, for some value c, there is a c for which f of c is 0. Now remember, I think I showed you before, this symbol means there is or there exists. Okay, so there exists a c so that f of c, this is not e, f of c is 0. Now I don't know how many there are, but I know at least there exists one. Now, using Rolle's theorem, I need to set the fact that at least I'm going to have 2 points in which the y's are the same. So the way that I'm going to use this theorem is by contradiction. So I'm trying to show that I'm only crossing the x-axis once. I'm trying to show that I only have one root, not several. So let's assume that I have 2. Okay, so I may have like okay, I may have 2, and then we're gonna see what we run into. So let's assume that I have 2 roots for this function. So if I have 2 roots, there are some numbers a here and b here for which f of a is the same as f of b, and that happens to be equal to 0. Okay, so by Rolle's theorem, if this is true, then there's gotta be a point between a and b for which the derivative is 0. So I'm gonna find f prime of x. F prime of x would be 3x squared, and the derivative of x is 1, and the derivative of minus 1 is 0. So now I just have to make this equal to 0. Now if I do that, then I have 3x squared equals -1, and then x squared equals -1/3. Now let's look at the reasonableness of this. There is no number square that gives me a negative value. So this is always bigger than 0 rather than 0 ever. This is always positive. X squared, the least number that it gets is 0. So this is always bigger than or equal to 1. So this is never 0. Never 0. So that means that if the derivative is never 0, then a point like this does not exist. This is in my imagination. So that means if a point like this does not exist, that means that I'm only touching the x-axis once and not twice. So this is how we are showing that there is no such a point. Okay, so there doesn't exist a c for which f prime of c is 0. So since it doesn't exist, then points a and b don't exist, so that means there is only one single root. And that's how we would argue something like that. This is just to explain how we can use the Rolle's theorem on showing different features of a graph. Now, going to the mean value theorem. The Rolle's theorem was used to prove this theorem, and let's explain what it means. we have to satisfy the following. F has to be continuous on the closed interval. F has to be differentiable on the open interval. And then the guarantee is that there is a number seen between AB for which the derivative is actually the same as the slope of the secant line. And remember from the bigger picture that I showed you, A and B will be here, then such points will be over here in my example, and then the slope of the secant line is this one. This is the slope of the secant line, difference of the y's over difference of the x's. And then there is a point somewhere in the middle, not exactly in the middle, but in between, in between A and B, for which the derivative is worth the same as the slope of the secant line. Now, this equivalent equation is it comes from just saying, okay, this is multiplying, so this quantity will, dividing, so this quantity will go to the other side multiplying. So these two are the same. You don't need to memorize both of them. It just can be written like this. It can be written like this. This is just looks like a line, like this is y minus y1 equals the slope x minus x1. It looks kind of like that. So there's a couple of examples here for functions going through points A and B. And then in here you have the difference of the y's as f of A minus f of B. And then in here you will have the difference of the x's, b minus a. And then you see how this slope is just the same as this other slope, and the slope of this tangent line would be f prime of c. Now we can have it with the slopes that are negative, or we can have them with the slopes that are positive. We can have them on functions that are quadratic, or you can have them with polynomials or trigonometric functions. In here we only have one c. In here we may have two c's. In here this is the secant line, and the slope would be difference of the y's or difference of the x's, and that is the same as the derivative at this point and the derivative at that point. So we may have more than one value for which the derivative is the same as the slope of that secant line. And this is the explanation that you can read on your own. It says, to illustrate the mean value theorem, let's consider this function on this closed interval. Okay, so remember that the domain in here would be all real numbers, but we're only setting this between 0 and 2. So between 0 and 2 we have that function f of 0 is 0, and f of 2 will be 2 cubed minus 2, and that will be 6. So in here 0, and then f of 2 will be 6 over here. Okay, for an example, a rough sketch. Okay. Alright, so it says there's gotta be a point in here. If this is the secant line through those 2 points, there's gotta be a point in here that has the same the slope of the tangent line to that point, the same as this secant line. And am I balling in here? If the secant line is going through this, then I'm thinking that this tangent line to this point would be a good approximation of it. So now the mean value theorem is not providing you with a specific way of finding it. It is just showing you the existence of it. So I know that the secant line is going to have slope difference of the y's over difference of the x's. So you can do that through it, or you can just write the equation f prime of c equals f of b minus f of a over b minus a. In this case, f of b is 6, f of a is 0 over 2 minus 0, and that would be 3. So I'm looking for some point whose derivative is going to be simply 3. So I know f prime of some c is 3. So now I just have to find what is f prime. If f is x cubed minus x, f prime of x would be 3x squared minus 1. So now I want to make this 3x squared minus 1 be worth 3. So now I solve plus 1 plus 1. So 3x squared equals 4. And then I divide by 3. And I have x squared equals square root of 4/3. Now, sorry, plus minus. And then this is plus minus 2 over rad 3, or plus minus 2 rad 3 over 3 when you rationalize. Now, x has two values. However, I'm only between 0 and 2. So the only value that actually fits between 0 and 2 is the positive one. So the value of c that I'm looking for, oh, I should have put c here. So the value of c that I'm looking for is the positive one, 2 rad 3 over 3. So for this value, f prime of this is worth 3, which is exactly the slope of the secant line through that. You can read the solution on the slide, or you can take my solution, that will be fine. As you can notice, my sketch was a little off. I showed you f of 0 and f of 2. I don't know what happened in between, but I know that there is a point that has derivative the same as the slope of the secant line here. So the derivative, the slope of the tangent line is the same as slope of secant line for this point, and it doesn't happen to be at 1. It's somewhere between 0 and 2, but it doesn't have to be the middle of 0 and 2. For example 5, it says, suppose that f of 0 is negative 3. So this is the point 0, negative 3. And the derivative of f for any point is less than or equal to 5. How large can f of 2 possibly be? So what they mean is, this is 2, but f of 2 is going to be somewhere in here. Okay. Now, if I put f of 2 very, very high, this secant line is going to give me a slope that is bigger than 5. So they are saying that the derivative for any point shouldn't be bigger than 5. If f of 2 is very high, the slope would be bigger than 5. Since I know Rolle's theorem, since I know mean value theorem, I know that for some point between 0 and 2, the derivative is going to be bigger than 5, and that's not what I want, because I don't know, I cannot go bigger than 5. If that was the case, then there's going to be a point between 0 and 2 whose derivative is going to be bigger than 5, because you know, the secant line is going to have a slope bigger than 5. So there's going to be a point that is going to have a tangent line that is parallel to this, so it's going to violate this. So f of 2 has to be reasonably low so that the maximum slope for a tangent line within it cannot pass 5. So I know that f prime of c for all c in the domain have to be less than or equal to 5. So that means that f of b minus f of a over b minus a has to be less than or equal to 5. Now, b in this case is 2, a in this case is 0. F of b is the one that I'm wondering about, and f of a is negative 3. So now negative minus negative 3 is plus 3, so it's f of b plus 3 over 2 less than or equal to 5. Multiply both sides of the inequality by 2, doesn't change the sign. F of b plus 3 less than or equal to 10, minus 3 on both sides, f of b less than or equal to 7. So that means, well, actually in this case it's f of 2. So f of 2 cannot go higher than 7. Can go up to 7. It could be over here, it could be over here. You don't know where you're going to place it. What you're saying is how large can f of 2 possibly be. So the largest that it can be is 7. If it's past 7, then I'm going to be forced to have some point in between that has a derivative bigger than 5, and I'm violating this condition. Now these theorems, this is something that it was already obvious to us before, but it is possible to say it now that we know mean value theorem. So it says if the derivative is 0 for all the x's in some interval, then f is a constant on that interval. So for example, no matter where the constant function is, it could be here, or it could be here, or it could be here, for all the points within, the derivative is 0. So that's something that it was obvious to us before. And then corollary 7, it says if the derivatives match for all the x's in an interval, then the difference of these functions is constant. Or in other words, one function is the same as the other function plus some number plus a constant. So for example, if f of x is 3x squared and g of x is 3x squared plus 6, I don't know if you agree with me, but the derivatives match, right? The derivative here would be 6x, and the derivative here would also be 6x. So the derivatives do match. So what's the difference between them? The difference between those two functions is simply a constant. And also graphically, what it means is that it doesn't matter how crazy my function f is. If I obtain f or I obtain another function g just by translating it vertically, not horizontally, vertically. If I move g, I don't know, if I move f 5 units down, so g is the same as f minus 5. If I move f down 5 units and I call that new function g, I know that for every x, the tangent line has the same slope for every x. So the derivative really doesn't change for any translation of a function in a vertical direction. For every x, I always have the same tangent line. When I'm shifting horizontally, then it is not the same, because if I were to move this f over here, let's say, for this x, the derivatives are not gonna match. I mean, there is a point here that you're gonna have the same tangent line, but it's gonna occur at a different x. So for the same x, it's not gonna be the same anymore. So only vertical translations, no horizontal translation. For vertical translations, the derivatives are always the same. What happens if I had f 3x squared and define g as 3x minus 3 squared? When I take the derivative of this, then it's gonna be 6x minus 3, and that will be 6x minus 18. And notice how the derivatives do not match anymore. So it doesn't match algebraically. It's not going to match graphically either. So only vertical translations, whenever the difference of two functions is a number, the derivatives are the same. Now, the example here, I know that this function, when I divide x by its absolute value, if x is positive, this is just worth 1. And if x is negative, this is worth negative 1. And it doesn't exist at 0 because I can't divide by 0. So what it's saying is that this doesn't contradict what we just saw. In this interval between 0 and infinity, the derivative is 0. And in here, in the interval negative infinity to 0, the derivative is also 0. But in the entire domain, I can't say that because the entire domain is not a single interval. But if I'm defining this interval, then the theorem is true, and then if I'm looking at this interval, the theorem is true. the theorem talks about intervals, it doesn't talk about the entire domain. So you have to define your interval to talk about the theorem, and that's all it says. So we're done, and let's get to practice. Yay!